What up, dudes? All right, let me also look at this thing I'm going to have. Yes, I'm going to start the recording. Let's get into this thing. It sounds like you folks are freaking out about this thing, and I don't blame you. Math is hard. But keep in mind that this should be Algebra 1 review. Like, you should be good at lines. So, if you're not good at lines, it's good that we reviewed it, because if not, you're going to just get crash and burn in this class. So we need to get good at this stuff before we move on. I do want to cover parabolas, and I think this is really important. As a physics major, I study things like these parabolas. This thing would be the shape of maybe the height versus time graph if you were to take something and throw it out the window. So I take something and I throw it out the window. That shape would look like what we call a parabola. Cool? All right. Well, you guys are complaining to me and saying, hey, I don't know my Algebra 1 because I skipped Algebra 1. Well, my answer to you is this. Well, if you skipped Algebra 1, it means you must have taken it already. Or it means you must really know your stuff. So don't complain to me about your, that thing. But anyway, let's move on. Let's go on to this. Check this out. I have a... Can you guys even see that? There we go. All right, there we go. Can you see that better? All right. So I have a function, and it goes negative 2x squared plus 6x plus 9. So what I want to know is this a quadratic equation or is it not? When we talk about quadratic equations, we're going to talk about it in the form like that equations that look like this. Ax squared plus bx plus c. It's going to have a number, x squared, plus some other number times x plus some other number. You've seen this before? Cool. And so ax squared plus bx plus c, this is called the standard form. Now, is this a parabola, 5x squared? Yes or no? Is that a parabola? Does this graph a parabola? And I'll tell you what, we're going to be working a lot with graphs. So here's what I'm going to do is I'm going to show you folks a very secret, very cool calculator to use. And I'll tell you why it's a really cool calculator to use. On my page, in general information, I have a link that says use this calculator from now on. It's a graphing calculator. So you want to click here, and it will pull up a graphing calculator for you. And it's not the coolest graphing calculator in the world, but it's super helpful, and I'll tell you why. Because this is the exact calculator that you will be given when you take the EOC exam. And that's pretty cool. All right, so let's graph that. I asked you, is 5x squared, is that a parabola? Let's graph it. So I put it in there. If I were to look at what the graph looks like, it looks like this. Is that a parabola? Yeah, that's a parabola. Very cool. Even though some of you were saying, hey, that's only part of a parabola. No, it's a full-on parabola. It's a parabola that looks like this. Like that. Now, in this case, what is A? What is the number? No, it's just the 5. The A is the number. Most people tell me 5x squared. No, it's just the 5. It's the coefficient. It's the number out in front. What is B in this particular case? 0. I don't see a B there. I don't see what is the... what I'm asking is, what is the number in front of the x? I don't even see an x all by itself, so there must have been a 0 out in front of it. Does that make sense? And what is the c in this case? 0 as well. Good. Yeah, so these, in the standard form of a parabola, b and c are allowed to be 0. Does that make sense? And then what happens if I had a c? Like, for example, if I had 5x squared plus 3. What would that graph look like? Is that still a parabola? That's my question.
Yeah.
Sure. And I'll tell you what, why don't we graph it and we'll check it out. Expression, I'm just going to add a plus 3 over here. I'm going to tell it to graph it. And there it is. I'm going to zoom up a little bit. Look, it's the same exact parabola. It's just moved up by 3. All right. So it'd be that. But my point is it still a parabola? Do you get it? All right, I got a question. What is this? 5x plus 3. Is that a parabola?
No.
No. What is the equation of?
It's a line.
It's a straight line. It's a straight line with slope of what? 5. And a intersect of what?
3.
3. So the graph would look like that. Right? So, what's the difference between this and this that makes the first one a parabola and the second one not a parabola?
The square.
The square, the to the second power. Cool. So if I go back to here and I ask you, is this a parabola, yes or no? That's all I want to know. Is it a parabola?
Yeah.
Check. Good. Is this one a parabola?
Yes.
No, it's not. Because of that 0 in front of the A for the A. Because that 0 will cancel out that thing, and really that equation is just negative x plus 12. That's not a parabola. The second one's not a parabola. Does that make sense to you?
Mm-hmm.
Okay. What about this third one? Is that a parabola?
Yeah.
Yes. What about this fourth one? Bradley, I'm not ignoring you, but what I am doing is, well, I'm purposely ignoring you, actually. I see your questions, and I don't think that you have the math for me to be able to answer that right now, so I'm kind of avoiding your question. But I do want to answer that question, but I'll get to it. All right. Is this one a parabola? X squared plus 15.
Yes.
What about this one? X squared plus the square root of 2x minus 4. Okay, I got a bunch of yeses. Yes, absolutely. What happens to be the b term in this case? The square root of 2. Or 1.41, I think. 1.4128, I think that's the square root of 2. I can't remember off the top of my head. What about this? F of x is equal to 6. Is that a parabola? No. Is it a line? What kind of line is it?
Horizontal.
Yeah, it's a horizontal line. It's a horizontal line at 6. Y equals 6. That's it. We cool? All right, let's try this one. What about this one? Is the second to the last one, is that a parabola?
Yeah.
Yes. What's A?
5. Negative 2.
Negative 25. It's the thing in front of the x squared term, so it's negative 25. What's, all right, the last one, 2x plus 3, is that a parabola?
No.
No, that's a straight line with a slope of 2 and an intercept of negative 3. Are we cool with that? All right. Let's analyze this, and we'll graph this a bunch of times, and we'll see what the difference is. All right, let's see. First of all, I want you to graph a parabola. Now, a parabola is, the most basic one I can think of is y equals x squared. And I'm going to make a quick table of this because, yes, by the way, Lucas, f of x is known as y. I'm going to make a table out of this. So I've got x and I've got y. And I'm going to plug in different values for x. So let's go with negative 3, negative 2, negative 1, 0, 1, 2, 3. We cool with this table? And then all I got to do is square the x. So negative 3 squared is 9. This is 4, 1, 0, 1, 4, 9. Did I go too fast for anyone? Okay. And if I were to plot that, at 0 it was 0, at 1 it was positive 1, at 2 it was 4, at 3 it was 9, 4, 5, 6, 7, 8, 9, way up here. And then the same, it's identical, or maybe what we call symmetrical. That would be my standard parabola. Are we cool with that? The graph is this U-shaped kind of thing. Now, I want to mess with the A. I want to mess with the A. Okay, wait. I need to talk about the domain or range. What is the domain of a parabola? Do you remember what the domain means? Do you remember that big thing I said about like my area? I love what you said there. It's my area, it's my den. So I remember what you guys did. What you remembered was when I said domain, you folks thought of that story I told you about like this is my house. Get out of my house, right? Do you remember that now? And that's why you're saying my area. It's because it's the values that I'm going to allow to come into my house. Does that make sense? So, or the values that I'm going to allow. Exactly. How can you forget it? And that's kind of why Mr. Dalde is so absurd when he teaches, is because I want you to remember this stuff. The domain is the values that is allowed to come in. Is there any values that is restricted of coming into a parabola? Lucas, can you not hear me? The answer is no. You can input any value into a parabola, and it's totally allowed. All right, now let's ask you this, because I think this is where Bradley's mind is going. What is the range? The range, if I'm restricting the inputs, then the range is a restriction on the outputs. Now here's my question is, are there any values of this parabola that is not allowed to come out? Looking at this specific parabola here. No, 5 is totally allowed. The 5 is totally allowed within the range. There we go, negatives, exactly. If you look at this, and I ask you, hey, for what x values is y equal to a negative number? And you would say, any x value. Because there is no x value that I can put in to make this thing, to make the y value be a negative number. You can see because the graph doesn't go below this line right here. Does that make sense? So there's a range restriction. And Sophia's actually exactly right, because, and Bradley's exactly right, because when everything is squared, it always becomes a positive. So it never becomes a negative. Does that make sense? So if I told you the range of this thing, that's actually telling you information of this thing. And that's where the range actually comes into play. Because when we're dealing with lines, it usually had no restrictions on the domain and the range. When we're dealing with parabolas, we have a restriction on the domain, or we have no restriction on the domain, but we do have a restriction often on the range. Does that make sense? It's like asking, if I were a basketball player and I was throwing this ball up in the air, like this, and up here is like 20 feet or something like that, and the question is, when does the ball reach 30 feet? And what would your answer be? Never. That's outside of the range. The range for this is between 0 and 20. You know what I mean? So, what you would say is does not exist because the range is between 0 and 20, and that's outside of the range, or something like that. That's kind of what I'm getting at here. So the parabolas have this thing that we call a range that's attributed to it, and it's important information. Let's graph these things right here. What I'm going to do is I'm going to duplicate this. I'm just going to copy this. I'm going to get a new tab, paste that. So I have two. Why didn't it copy? Copy that. Paste that. There we go. I have two calculators. What? Error in initializing calculator. All right, here we go. I'm going to just open up the calculator again. There we go. All right, here's what I'm going to do. I'm going to take two calculators. I'm going to put them side by side. All right. Now, on one of them, I'm going to graph x squared. Got it? On the other one, I'm going to graph 2x squared. And I want you to tell me which the difference is. Here, wait. Okay. I graphed x squared, and then I graphed 2x squared. And I'll be honest with you, Sophia. To be honest with you, I hate to say this, but you don't learn about what B and C means. In fact, that's not even in the curriculum. But I do think it's interesting, and I will give you something on that later on, maybe next week. That's actually an advanced question. You learn about different parameters, and for this parameter, we're learning about the a in the ax squared. If the a is a number like 2, what happens to the graph? And some people say the right is tighter. Some other people say it's steeper. Okay. Do you guys know the right way to eat gummy bears? How do you eat gummy bears?
The whole thing.
Okay, here's what I do. You just pop it in your mouth?
Yeah.
How boring are you? There's a right way to eat gummy bears. You want to know? Okay, I wish I had some gummy bears right now. Actually, I think I might keep some gummy bears. Usually I have. Sometimes I have gummy bears in my thing. Yeah. All right. I'm kind of on the page of Kealaka. Is that how you pronounce the name, Kealaka? Is there a short version there? Oh, Keala. Kai. All right, Kai's good. All right. Yes, I'm on the same page. I torture my gummy bears before I eat them. You don't do that? Really? What kind of sick person are you? Yeah. See, I do one of two things. I take the gummy bear, and I hold it with two hands. I grab the head in one hand, and I grab the feet in the other hand, and I say, "No, please, don't hurt me," and I pull it apart, right? And you pull it and you stretch it until it pops off, and you pop the head off, and then you pop the head in your mouth, and you pop the body in your mouth. That's how you eat gummy bears. Come on, you know you've done that, right? Now, when you pull gummy bears apart and say, "No, please, don't hurt me," what happens to the gummy bears? Does it get fatter or skinnier?
Skinny.
If I'm stretching it vertically, does it get skinnier? It gets skinny. Good. You folks are wondering, what kind of twisted math thing is Mr. Daldy trying to teach me now? And my answer is this. I actually have a point. It's a good point, too. My good point that I'm trying to make is that what is happening to this parabola is, I call it getting vertically stretched. And some people would say it gets skinnier, and I don't like thinking of it as getting skinnier. But yes, I agree. That is a result of being vertically stretched. This parabola is like a gummy bear that is being vertically stretched. And when it gets vertically stretched, it gets skinnier. And how do I know it's getting vertically stretched? Well, let me show you. If I were to graph, instead of 2x squared, let's graph 5x squared, and we'll see what that graph looks like. What happened? It got vertically stretched even more than the 2x squared. So the number a, if it's a big number, what happens to the parabola?
Super thin.
It gets thin. And the bigger the number, what?
It's more wide.
The thinner it gets. And what I liked, instead of thinking of it as the thinner it gets, I like thinking of it as this idea of getting the A, or of vertically stretching it. And Sophia's asking why. And I love the why question. And my reason is this. Because what you're doing is, all right, I'm going to erase this thing right here. All right. So let me show Sophia what's going on here. What I'm going to graph is, I have my table over here. Got it? I'm going to graph another one. I'm going to call it k of x, which is equal to 2 times y. So all I got to do is I got to multiply this number right here by 2. So this is 18, 8, 1, or 2, 0, 2, 8, and 18. Are we cool? So let me go back to graphing that parabola. Let's say the parabola looks like this. 1, 2, 3, 6, 7, 18. All right. So the original parabola looked like this. 1, 1, 2, 4, 3, 9. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. This is the original parabola. Got it? Now, the new parabola went at 3, it went to 18, so way up here. And at 4, it went to 8, so right about here. And then at 1, it went to 2. And at 0, it stayed at 0 because 0 times 2 is 0. And then it repeats itself in a kind of a symmetric pattern. So what it did was it kind of had to keep its vertex at the same spot, but it kind of like stretched everything up, amplified by a factor of 2. Does that make sense to you now? So you can see why that number will vertically stretch something. All right. What do you think if putting that number in front vertically stretches it? What do you think putting a negative in front will do? So instead of x squared, I'll have negative 1 x squared. Do you think it's going to flatten it out? It's going to make it a fat one?
Flip it, like go down, like upside down.
What a negative does, and this is what a lot of people have trouble with, is what a negative does is it doesn't fatten a parabola out. What it does is it takes it and flips it over. Anytime that number a is a negative number, it takes your parabola and makes it a sad face parabola. So here's a happy face parabola. You see the happy face? And here's the sad face parabola because it has a negative in front of it. Are we cool with that?
Yeah.
Yes, awesome. Good. Then that's pretty easy. All right, I got a question. Then how do I make, we talked about how to get that parabola on the slim fast plan or maybe the torture device where they stretch them, right? How do you make a parabola fatter? And I don't want to say fatter because that's not PC. So how do you make a parabola, like the other way to eat gummy bears is you squish them between your fingers, right? You put them between 2 fingers. All right, Lucas is saying 0.1. All right, let's try it. Tell me the difference between the parabola on the left and the parabola on the right. What's the difference? Yes, exactly. It got wider. Very good. So it got fatter or wider, or what I like to say, since I like, to be politically correct, is it's like getting vertically getting vertically compressed. And when it gets vertically compressed, when you vertically compress a gummy bear, it gets fatter, right? It gets shorter and fatter. Which apparently maybe somebody like vertically compressed me because I'm short and fat. But anyway, that's neither here nor there. All right. Yeah, those were popular back in the 90s. Okay, so we talked about, because what's important is, what I need to talk about is instead of 1/10 or 0.1, really that's the same as 1 divided by 10. That's the same thing that you graph. So what Lucas was suggesting is a fraction, like let's say 1/2. That looks like a pretty good parabola, but when you compare it to this parabola, you see that, it's still a little bit fatter. Does that make sense? Yeah. So really what you have is when a is a fraction between 0 and 1, because any number between 0 and 1 is a fraction, right? Or not any number, but most numbers between 0 and 1 are fractions, but it doesn't only need to be a fraction. But if a is a number between 0 and 1, then it's a fatter parabola or a vertically compressed parabola. Versus if it's a number bigger than 1, it is a vertically stretched parabola, making it skinnier than the standard parabola. And if a is negative, then it flips it upside down. We cool? All right, let's try this one then. So I think I covered for you if I have 2x squared, what happened to that parabola? 2x squared. What happened to this parabola? It got bigger than just x squared. Yeah, you need to say what you mean by bigger.
Stretched vertical.
It's got vertically stretched. It didn't get wider, it got skinnier actually. Because when you vertically stretch like the rack does to a gummy bear, it makes it skinny. All right, now this parabola over here, what did that do? You can answer if you want.
Wait, which one?
This one that I'm pointing at right here.
It got fatter.
It got wider,
Or wider.
or what I like to think of it is it got vertically compressed. All right, now what happened over here?
Upside down.
Not only is it upside down, it's also vertically stretched. So I like thinking of it as a regular parabola that is vertically stretched by a factor of 2 and flipped upside down. Actually, Sophia, you're getting it a little backwards. This parabola that I'm pointing to at right now is not vertically challenged. It's actually vertically blessed because you're stretching it. This one over here is vertically challenged. This one over here is vertically stretched. Cool? All right.
So if it's a negative fraction, then it's like
So,
upside down. And like
okay, so Emily's asking, what happens if it's a negative and a fraction? Well, the fraction does what?
makes it wider.
It makes it wider. The negative does what? Turns it upside down. Exactly. That's exactly what happens. You folks are right. All right. Let's graph these. 1x squared plus 1, 2x squared minus 1, negative 2x squared plus 3. All right, here we go. And we'll talk about it. So what I'm doing is I'm teaching you this math, which should be reviewed to you, but I'm teaching you this math through just kind of like saying, well, let's practice it. Let's try it and see what the difference is. What I want to do is I want to kind of explore these things with you rather than just tell you them. Okay, let's try this one. I'm going to do, I graphed x squared, that one's the one on the left, x squared, and then over here I'm going to have x squared plus 1. What is the graph on the right going to look like?
Just one up. Right?
Move one up. So all it is it's the exact same parabola. The only difference is I took that whole parabola and I pushed him up on the y-axis. Does that make sense? So yes, Sophia, in this case, C does move it up or down. So when Bradley asked, well, what does B and C do? Because we explored all of the things that A does. A makes it skinnier, it makes it fatter, and it flips it upside down. C moves it up and down. What does B do? Does B move it to the right and left? And my answer is kind of. It's not as straightforward. B is a little bit funky. And in regular math books, we don't even teach you what B does. And I know what it does. And it still is a little bit funky, but it's maybe something you should play with. And I'll give you homework on that one later. Don't worry about that. All right? But for now, just stick with what I'm teaching you now. All right, so this C will move it up and down. So what if I have a negative 1? What does that do?
Down one.
It takes that graph and it pulls the parabola down 1 unit. We cool? All right, so before I even graph it, here's what I want you to do. I want you to tell me, what is this graph going to look like? Right here. 2x squared minus 1.
Upside down parabola that's stretched vertically.
Emily says it's a stretched vertically parabola
By
and
2.
upside down.
And it starts at -1, the vertex.
All right, I completely disagree with Emily. All right, let's see. It's stretched vertically. It's right side up. Sophia's saying it's kind of wide, upward facing. Okay, Bradley's actually completely correct. This parabola. Well, actually, you know what? Let's graph it and we'll see. This parabola is stretched vertically. It's not upside down. It's got skinnier, and it got pulled down 1 unit.
But it has a negative right there.
No, the negative is on the -1, not on the a. The a is the number in front of the x squared term. Does that make sense?
Yeah.
All right, I got a question, because Genesis, I love how you ask me lots of questions. However, I haven't seen you ask me any questions yet. Are you completely lost, or are you getting this? Yes, Bradley, I completely agree. It only flips it upside down if the a is negative. In this particular equation, the c was negative. Does that make sense? All right. And Genesis, I'm still asking you a question. How are we doing with this? In fact, I'm going to ask everybody this. Let's take a temperature check. Are we hot, cold, medium? Type it in. I want to know. By cold, I mean like you don't understand it. I don't mean you're physically cold and cool in an air-conditioned room. Oh. All right. Oh, by hot, I mean you understand. You understand it, right? So, okay, good. All right, let's look at this graph right here. What does that graph look like?
Okay, that's a negative, right?
All right, that one is negative, so it's a parabola that's upside down. What else?
And it starts at 3.
It starts at 3. That means it's pushed up 3. And what does the 2 do?
Stretched vertically.
All right, Lucas says it widens. Sophia says it thins. Okay, Bradley says it thins. Lucas now says it thins. Yes, it does thin because of that 2. If we were to graph that, that would be a -2 in front of there, and then we'll put a +3 over here. So, the graphing calculator I'm using is not the best graphing calculator in the world. I'd rather you folks use like better graphing calculators. However, I mean, not I'd rather, but I want you to use this graphing calculator as opposed to a better graphing calculator, because this is the one you'll get on the test. So if you get used to it now, boom, you're good. Cool? All right. I think that I technically should be done. Let's see. Let's talk a little bit more about this stuff. All right. Summary. The effects of different values of a and b have on a graph of g of x equals ax squared plus c. Okay. Changing the value of a in g of x equals ax squared simply increases the height of the parent function defined by f of x equals x squared. So basically they're saying compare it to the regular parabola x squared, and if you increase the a, it increases the height of it, which I like to think of it as vertically stretching it. The factor of a, provided that a is positive. Okay, thus g of x equals 3x squared will grow faster than the parent function 1/2 x squared. So basically they're comparing 3 of x squared to 1/2 of x squared, and they're saying one grows faster and one doesn't grow as fast, so this one's short and fat. Cool? The vertex, however, will remain the same if you change a. Negative values of a will basically reflect the parent function across the x-axis. It will flip it upside down. That's what it's saying. The vertex will remain the same, but it is now a maximum instead of a minimum. And what they mean by that is they're saying this. If I were to ask you, what is the minimum of this graph? Let's pretend it crosses right here. What is the minimum of that graph? What would you say? 0. Very good. Now, if I were to ask you, what is the maximum of that graph? What is the highest point to which it goes? Infinity, exactly. So this graph right here does not have a maximum. It only has a minimum. Does that make sense? Whereas a negative parabola, something that looks like this, that has a maximum, but it doesn't have a minimum value. Are we cool with that? Now, I think that my last thing I'm going to talk to you folks about before we leave is the motivation for why we're learning parabolas. My answer is this. Look, maybe not all of you are going to grow up to be physicists. However, I would hope at least one of you do. Because they're on the SATs. Yeah, but what does the SAT really do? I don't know. But so what I'm saying is this. A lot of times people see parabolas in business. And I'm sure that even if you're not going to be a physicist or an engineer or a mathematician or whatever, you will be interested in making money. And so since you be interested in making money, what you would want to do is, like, let's say your graph actually ends up looking like this, and this is how much money you make. What you always want to try to do is you want to try to optimize whatever this is, so you can make your y value at the highest point right here. You don't want to change this x value so that you make your y value over here or over here. You want it to be the best possible amount. Does that make sense? So, in order to know that, you need to know about these parabolas. In fact, this idea that I just showed you is pretty much the whole concept behind calculus and why we came into calculus. So this is kind of where we're going to. Not to say that you're going to take calculus, but I mean, I want you to understand at least the basics of this, and that's Algebra 2. Are we cool? So there's your motivation. Let me just kind of preview for myself what's coming up. Let's see. That looks like a good warm-up for us. That's pretty good. Oh, laws of exponents. We'll probably start off on that stuff later, right after. All right. So we got to finish off chapter 2. Not today, but we'll do it on Monday. At this point, I'm going to stop the video, and I'm going to maybe record a different video